NPTEL lecture on earthquake resistant design of foundations. This is 29th lecture on this ERD of foundations, and we are continuing with the 4th module of the course, that is on the well foundations. So you could see that within the well foundations, we have covered these topics: introduction, which is already over. Second part, that is lateral stability of well foundations. Almost we have done with that, and today we are going to discuss the remaining part of that. And then today we will also talk about how to construction and sinking of a well. Finally, then in the next lecture we will discuss the last two topics, that is tilting and shifting of wells and some numerical problems. So let's start from lateral stability of well foundations. As discussed in the last lecture, in 28th lectures, there are 4 different methods for lateral stability of wells. Tarjhaji, we have discussed in detail. Pender and Banerjee and Gangopadhyay, that is also discussed. And the last method, that is the 4th method, is by Indian Road Congress, called IRC method, which is from IRC 45, 1972, and formulated recommendation for well in a cohesionless soil to estimate soil resistance below maximum score level. And there are 2 methods of IRC. One is elastic theory method, which we have discussed in the last lecture. Today we are going to talk ultimate soil resistance method of IRC method. So let's start with ultimate soil resistance method. And you see in the ultimate soil resistance, on the basis of elastic theory, the pressure on the sides and at the base under design loads were determined. However, to determine the actual factor of safety against failure, calculation of ultimate soil resistance is necessary. For checking the ultimate load capacity of a well foundation, the applied loads are increased by multiplying them with suitable load factors, and which is for various load combinations, and the ultimate resistance is reduced by appropriate strength factors, and the two are compared. So what is done here? The loads are multiplied by some factor, while the resistance is reduced by appropriate strength factors. So 2 things will be done. So continue with that. So these are the steps. What are the steps for the ultimate soil resistance method? The first step, compute the applied loads for various combination of load factors as given in the slide. So there are 6 different combinations has been given here. First is 1.1 times D, and then second, third, fourth, and like this. So you have here 5 combinations, and out of these 5 combinations, what is D here? D is called dead load. L is live load including braking effect. B is buoyancy. WC water current force. EP is earth pressure force. W is wind force, and S is seismic force. Here, as usual, you know that out of wind force or seismic force, only one of them is considered. We don't consider wind force and seismic force together, as usual. So out of these 5 combinations with load factors, different load factors for different types of load, whichever give you the worst combination, that need to be considered in the analysis. So the method assumes, in this method, which is on ultimate soil resistance method, it assumes the point of rotation is at a height of 0.2 times the depth of well above the base of well, which we'll discuss later. And the bending moment should therefore be computed at the point of rotation instead at the base. So first thing is that it assumes that point of rotation is not at the base, rather at a height of 0.2 times the depth of the well. So continue with that. So step 2 is here. The first step need to be applied in the step 2. Once you have calculated the load, then maximum average pressure at the base, which is total load, downward load acting at the base of the well, including the self weight of the well, increased by suitable load factors as discussed in step 1. Once you know the value of W, then it should be divided by the area of the base of the well. So you get the pressure at the base, and this pressure should not be that Q greater than QU by 2. What is QU here? Ultimate bearing capacity of the soil below the well base. So once you get the ultimate bearing capacity of the soil below the base, half of that, that is the factor of safety 2 for ultimate bearing capacity, which will be your set bearing capacity, then that pressure coming at the base should not be more than that. So this is the first check. Suppose this check is not satisfied, in that case the diameter of the well should be increased if this condition is not satisfied. So this was step 2. Now in step 3, you calculate the resisting moment at the base which is denoted m subscript b at the plane of rotation. And this resisting moment is given by the relation QWB into 10 phi, where B is the width parallel to the direction of forces in the case of square and rectangular wells or diameter of circular well. So it will be a width in case of in square case you can have width or length is same, but in rectangular case it will be width parallel to the direction of forces. And or if you have circular well, then B should be taken as diameter of the circular well. Q is a constant which depends on the shape of the well and the ratio of the depth to width B. So for a circular base, a shape factor of 0.6 shall be used, but for rectangular wells, Q depends on D by B ratio, and this value of Q lies between 0.41 to 0.64, depending on D by B. Suppose D by B equal to 1, then it will be 0.45. If D by B is increasing, then the value of Q is increasing, but the value of Q will be always less than 1. That is need to be understood. And phi is the angle of internal friction. So using equation 3, one can calculate the value of resisting moment at the base. Continue with this. In step 4, what we calculate the two moments. One is called on the surface and another is at the base. So compute the ultimate moment of resistance on sides of the well, and the moment of resistance is due to first is passive soil resistance Ms and frictional resistance Mf. So what you have, passive soil resistance Ms is given by the relation 4, where for frictional resistance is given by equation 5 or 6. Equation 5 will be applicable for rectangular wells, while equation 6 will be applicable for circular wells. In these equations, gamma is unit weight of soil. L, which is coming here, is projected width of soil mass offering resistance. For circular wells, it will be 0.9 times the diameter, while D is grip length below maximum score level, which is also called depth of well foundation. I emphasize again here that capital D in all these well foundations is not the diameter of the well, rather it is used as the depth of the well foundation. So capital D will be depth of well foundation, and that was the same thing in case of Tarjagi's theory also. Now, what is Kp and Ka? They are active and passive coefficient of earth pressure to be calculated using Coulomb's theory. So K is active and Kp is passive earth pressure coefficient. Delta is the angle of wall friction, which is taken as 2/3 of phi, where phi is the angle of internal friction, but the maximum value of delta should be taken 22.5 degree. For example, if you have phi equal to 30 degrees, then 2/3 of phi will be 20, then it's fine. But if you have phi equal to, let's say, 36 degree, then it will be 24 degree, 2/3, but we need to take the maximum value, upper limit is 22.5 degree. So in equation 4, 5, 6, you calculate Ms and Mf. Mb is already calculated. So we sum up all these moments applied. So the applied ultimate bending moment M should be compared with the total moment of resistance. What you have, Mb plus Ms plus Mf, all these combination will give the resisting moment, and this resisting moment should be multiplied by factor 0.7, which is kind of a strength factor. And so you get the total value resistance moment Mr, and this Mr should not be less than the applied moment, or you can say that applied moment should not be greater than Mr. Okay, so we need to apply this check also, that the value of Mr should be less than should not be less than M. Okay, and if this condition is not satisfied, in that case the grip length of the well needs to be increased and computation is redone. The equation used in the plastic theory. So let's see that these equations which are coming, how they have been derived, we will discuss in briefly. First of all, basic resisting moment MB is the moment due to the frictional force developed along the rupture surface at the base. MB is the resisting moment at the base. And this rupture surface for square wells is assumed to be cylindrical, passing through the corner of the wells. For circular wells, the surface of the rupture is assumed to be a part of a sphere with its center the point of rotation, and passing through the periphery of the base. So it is explained in this figure. So you could see what is shown in this figure. You have a cylindrical valve. The depth of the valve is D, capital D, and H is the height of the score level from the ground level, small h. Then what you have, the O is here set as a point of rotation, and R is the radius of this valve, cylindrical valve, and this point of rotation is at a height ND, where N is normally 0.2 as discussed later also. And this is the plan of the valve, where width of the valve is B and length of the valve is L. So that means its cross section is rectangular, not the circular. And then what you have here is shown is the forces acting from applied load, which is per unit width will be W divided by B, where B is the width of the valve foundation, and upward base pressure for unit width is also same. So here W is the total vertical load, taking into account the modification due to load factors. The load per unit width will be W by B, which will be equal to the upward pressure. Considering a small arc of length at an angle alpha from the vertical axis, the vertical component of force on element is given by this relation RD alpha cos alpha WB. Okay, and ultimate soil resistance method. So what you have in the ultimate soil resistance method, the forces, which is the normal force developed at the element due to vertical force, is given by this relation dFn W by B RD alpha cos alpha cos alpha. So in this case, what you have this the value of this is for particular slide, okay, and this should be, because this is a component, this force, and the cos alpha is its component. Now to calculate the value of n, it should be integrated from 0 to theta. Once you do this integration, then you end up in this equation RWB theta plus sin theta cos theta. Now the value of sin theta and cos theta are given from these relations, and if you once you got the sin theta and cos theta from this figure B by 2R and ND by R, then tan theta can be found from this relation, and R will be simply the, you can sin square theta plus cos square theta will be 1, and then R can be calculated. And once we substitute all these back in equation 9a, then you get equation 9c. All right, continue with that. The moment of resistance of the base about the point of resistance MB is given by this relation, where MB is F1 tan phi into R, okay, where IRC 45 method recommends a multiplication factor of 0.6 to equation 10 to account for the surface of rupture being a part of a sphere. All right. In both the cases, assuming the point of rotation at point 2 times D as shown here, the moment of resistance of the base can be expressed by the equation 11, where it is tan phi as it is. Fn is this F1 into R is replaced by Q into WB. So ultimately the moment of resistance is given from this relation, and this B is width of parallel, which we have already discussed, and for circular base Q should be 0.6, otherwise Q need to be calculated from the table. Continue with that. Now continue with this derivation part, side resistance MS, how to calculate the side resistance MS, and then the friction force MS. So for calculation, first thing is here that it is assumed in this case that the point of rotation O is at a height 0.2 times D here as shown in this figure. Now when we extend this OD, so it cut at E, and you have D1. D1 is this height, let's say, and D is the total depth of valve foundation. From similarity of triangles, D1 will be 1/3 of the total D, okay, because this is this will be D1 will be 1/3 of D. That means it will be at the, if we put this, so it will be at the centroid of this. Now taking moment of forces about the point of rotation O, moment per unit width is calculated from this relation, which is 0.096 is roughly 0.1 gamma d kp minus ka. This is for a unit width. For a width of L, the moment can be calculated from this relation. And for when we to calculate the value of MF, what is total friction force per unit width is area of triangle AOE shown here plus area of triangle BOD multiplied by sine delta. So all the numbers have been put it here, and finally total frictional per unit width is calculated in equation this, and we get this for a rectangular valve of width L. The moment about the center of rotation is given by this relation 1.1 by 3 gamma d Kp minus Ks V by 2. So once you simplify it, you get 0.183, roughly 0.180 gamma Kp minus K LBD square sine delta. While for friction, for circular valve, this equation get hold 1 by 1.13 and gamma d cube. So you have this for a circular valve, where B will be the diameter of the valve and L is the projected width. Then for circular valve, L is taken as 0.9 B. But for a rectangular valve, this equation will be given by from this relation, which is given in 0.11 gamma Kp minus Ka. So this is coming basically once you do for circular, once you put this number here. So this was for a rectangular valve, and then you got when you put L equal to 0.9 B in this equation, then this equations become for the circular valve. So this was for the circular valve, and this top one is for rectangular valve. So this continues this. Now let's discuss the construction and sinking of a valve. Construction of valve foundation consists of the following 5 stages. First is laying the cutting edge. Second, alignment control. Third, construction of valve curve. Fourth, construction of valve staining, and finally valve sinking. So let's discuss one by one. Laying the cutting edge. Valve foundations are constructed in stages by sinking under self weight, as well as dredging the soil inside the dredge hole and on the sides outside. The first step in the construction of valve foundation is to lay the cutting edge and valve curve. If the river bed is dry, the cutting edge is placed in position after removing the top loose layer of sand. The second stage, which is alignment control, the center line of the valve should coincide with the center line of the abutments and piers and of the bridge. Masonry pillars are constructed on the center line of the bridge to serve as station points for checking the alignment of the abutments and piers. Third stage, construction of valve curve. The valve curve is assembled on wooden blocks or sandbags placed at suitable intervals so that it doesn't sink while assembling the curve. Concreting is done after placing the reinforcement. M15 or richer grade concrete is used for the valve curve. The valve curve is then allowed to set for a week before sinking is started. The valve curve is allowed to sink alone before raising the staining above it. So before you start the construction of staining, the valve curve should be finished. Now fourth stage, which is the major stage, that is the construction of valve staining. As we discussed, that valve staining is the measure or body of the valve, and this is the main body of the valve. The grip length of the valve is very small at the beginning of the sinking operation, and the chances for tilting are more. Therefore, the staining should not be raised too high in the initial stage of valve sinking, which would otherwise lead to increasing the tilting further. Hence, the valve curve is first allowed to sink alone, and the staining is then raised in small heights of 1.5 meter at a time, allowing minimum 24 hours before adding the next height of the staining. So initially, the first stage, once we have done with the valve curve, the next is the raising the staining. The initially height, it should be at only in a small height of 1.5 meter. And once you raise for 1.5 meter, then at least it should be allowed to for 24 hours so that it gets strength before the adding the next height of the staining. The staining can be raised in installments of about 3 meter once the valve has sunk to a sufficient depth to get a minimum grip length of 6 meter. So once the valve is sink to 6 meter, then we can increase the staining in a increment of 3 meter. Before that, increment should not be more than 1.5 meter. The staining machinery should be constructed perfectly vertical to ensure vertical sinking of the valve. Strays of the about 2 meter length should be used for this purpose along the outer periphery of the staining at suitable intervals. When the staining is raised by this height, the straight edges are removed and fixed at a higher level, and the entire height of the staining should be raised using this procedure. Now the well sinking. The soil in the drainage hole is excavated to facilitate sinking of the well. A large size spade known as jam is used for excavation underwater, and this jam consists of a sector shaped steel pan with edges connected by rope and wooden pulleys. When jam is used, excavation is done manually, hence well sinking is slow. Alternatively, automatic grabs or dredgers can be used for excavation operated by a winch and a crane. Many times what is called Bell's dredger is commonly used for sandy soils. As the sinking proceeds, more the depth of the well foundation will be below the scour level, increasing the frictional resistance between the staining surface and the surrounding soil. The staining is loaded with what is called the net layers through a suitable platform and with sandbags piled on it to add well sinking, overcoming this frictional resistance. The platform for the net layers is constructed in such a way that it doesn't obstruct the dredging process. Air and water jets are also used in addition to the net layers to further overcome the frictional resistance, and these jets consist of GI pipes of 2.5 to 5 centimeter diameter with a nozzle at one end. So this was the stage 5 where wells, which was related to well sinking. So in summary, well sinking may stop and tilting may also occur when the cutting edge encounters an obstruction below it. The obstruction can be removed by dewatering the well using what is called pulsometer pumps and blowing the sand into it. The dewatering process should be continuously washed and should be suspended if there is a tendency for tilting of the well. Dewatering also should not be used unless the well has sunk to a sufficient length of minimum of 9 meters. Okay, so at least the well is already sunk to 9 meters, then only one should use the dewatering. These are the references. Most of the material are taken from the first reference, which is by a book by Gopal Ranjan and Rao, Basic and Applied Soil Mechanics, and is in India International. Okay, so this resource material is gratefully acknowledged, and speaker is thankful to the authors for such a nice, excellent literature. So with that, I conclude for today's lecture. Thank you very much.